Hey there, folks. Welcome back to class. According to my calculations, it should be September 14th. We're going to be in chapter 6 of the book today. We're going to be looking at our first of three different types of rocks, as you already know. We're going to be looking at igneous rocks. Igneous rocks, of course, are frozen rocks made from molten material, and it's part of the rock cycle. So, so one of the bad things, about having to do everything online is the fact that I'm kind of a rock nut. So I've got lots and lots of rocks, and I usually bring crates of them to class and let you touch them and feel them and look at them. Uh, and I can't do that now. So I'm going to show you some on the video. They won't be nearly as dramatic as being able to see them in class, but we'll look at them here all the same. So the first rock I'll show you is this one here, which is even on video is not very pretty, right? But this is literally a piece of frozen lava. So this was lava, came straight out of a volcano or something, and then froze or solidified into a piece of obsidian. So this would be something that we'd call obsidian. And I know it's kind of hard to see. If I could do it this way, you can kind of see it looks kind of shiny, almost like glass. That's because it is almost like glass. Then if you look at it more closely, you'll also see lots of holes there. They almost look like little craters. Look like this is on the moon, and it was little craters. But the holes are literally what we call vesicles that are the gas. So there was gas inside the lava when it was coming out of the volcano. And as the gas came out and the bubble kind of popped, the gas bubble kind of popped, it left that hole. And so you can see this was literally liquid at one time and cooled very quickly and became, again, almost like glass. I'll tell you a little bit more story about that in just a minute. Then the other things I was going to show you, I'll show you the whole bunch of them. This is kind of a thing I brought back from Maine, and I call this my bowl of granite. Okay, so there's a whole bunch of granite stones in here, and if you could see it, and again, I usually bring it and let people look at it, but if you could see it, all the little granite stones in here are all very different. So here's one that's kind of a whitish color with some black specks. This one's kind of more of a red color, if you can see that. Some of them, and we'll talk about this in just a little bit, some of them, the crystals inside, the specks inside are big. Like this one here, you can see the specks are pretty big, whereas the specks on this one are quite a bit smaller, and we'll talk about why that occurs in just a little bit. But I got a whole bowl of granite here, and literally that came from Maine, and I got these off of a beach. So that's what the sand looks like in Maine in some places. It's not sand, little bitty sand pieces, but sand rocks. So anyway, let's jump into chapter 6, and like I said, we'll get back to our chapter, and if I don't forget, I'll tell you the story about my piece of obsidian. So here's the book. Here we are in chapter 6. Up from the Inferno, magma and igneous rocks. And I hope this thing doesn't lag around like it does normally. So here we go. So in the introduction, it talks basically about what igneous rocks are, where they come from, and it talks about the fact that they are literally frozen melts. So melts are where molten rock, again, when it's under the ground, we call it magma. As it comes out of the ground from a volcano or some sort of volcanic activity, and it comes up out of the ground, we call it lava. So all that stuff you see, the pictures of Hawaii where you see that red glowing rock coming out of the ground, that would be lava. And again, Hawaii is a good example, but you can see that lava flowing. It almost looks like a river. Sometimes it almost looks like a river of water, and it's almost moving that fast. So it's magma when it's under the ground, and it's lava when it's on top of the ground. Here we can see where some of that lava is moving across the surface. And again, it sometimes goes very quickly when it's very hot, but as it cools, as you can imagine, it begins to slow down. We say it gets more viscous. We'll talk about that in just a little bit later. And this is called pyroclastic debris. So I guess it's the people up north, the Inuit people have like 20 different names for ice. The Hawaiian people have many, many names for lava. So there's different kinds of lava. And we'll talk about that a little bit more detail when we get to chapter 9. We're talking about volcanoes. So anyway, go ahead and read this chapter. One of the big issues here, or one of the things we're going to look at when we talk about types of rocks from igneous rocks, are whether those rocks are extrusive or intrusive. So the piece of obsidian that I showed you, the literally frozen lava, is an extrusive rock. So it was magma that made it to the surface as lava and then cooled very, very quickly on the surface outside of the Earth's crust, so it was extrusive. However, most of the, actually all of the granite that I showed you is an intrusive rock. So in other words, it was molten under the ground. It never actually became lava. It stayed magma, but it reached a point somewhere near the surface, and depending on where that was, it froze, cooled off and froze, and became what we know as granite. But it's an intrusive rock. And so those are the two big distinctions between igneous rocks. So if someone shows you an igneous rock, you have to sort of make a determination as to whether or not it's an extrusive igneous rock or an intrusive one. Did it freeze outside of the Earth's crust, or did it freeze inside of the Earth's crust? And we'll talk a little bit more detail about kind of how to make that distinction here in a little bit. I think if you looked at the rocks carefully, you probably already have a guess as to what that might be. So anyway, your book goes on to talk a little bit more about volcanoes, and it asks a question about, well, why is the Earth hot inside? And we know from the formation of the Earth that those bombardments of planetesimals that eventually created the Earth and the size of the Earth based on the number of planetesimals that hit as they land, almost like meteors. They release energy, and that energy is released as heat. And so the Earth probably started heating up as it was being formed, probably at least a few times in its history. The Earth itself was probably just one big lake of lava. It was probably so hot that, in fact, there was no, or very little, frozen material on the surface. It was all lava. So you could almost say that all the rock that is, well, you can't say, all the rock that is actually started out billions of years ago as igneous rock, and then has changed over time, as we will see when we start talking about the other types of rock. And so that's where these rocks came from. Now, why is the Earth still hot? That's another interesting question, and one that scientists debated for a long time until they realized that, in fact, there's a lot of radioactive material inside the Earth. And radioactive material, as we will see or have already talked about in a little bit of detail, but radioactive material, as it breaks down, releases energy in the form of heat. And so a lot of the heat now, 4.6 billion years after the formation of the Earth, a lot of that heat now didn't come from those planetesimals. It's not left over from the formation of the Earth, but most of that heat now is the result of radioactive decay inside the Earth. And so here you can see some pictures of volcanic formation. Volcanoes are formed over these magma chambers, and we'll look at when they freeze, they become what we call plutons, big domes of rock, and sometimes those plutons will erode, and or the stuff above it erodes, and we see them above the surface, and it's pretty impressive. But this is how these volcanoes form. We can see parts of them in some of these layers. In other words, there we can see a lava flow and a pyroclastic flow of lava. And then a lot of times we see these things called dikes, and basalt is another form of an extrusive frozen igneous rock that forms in these cracks and stuff in other kinds of bedrock, and so they will form these what we call dikes inside rock, and they'll get exposed too with erosion and that sort of thing. So the causes of melting, again, we've kind of gone into it. There's, you don't have to know all the different types, but there's changes in pressure can cause melting. When hotter rock gets closer to less hot rock, it can give it that energy, and that rock that was solid a little while ago can melt and become a magma that could be make its way to the surface as lava and eventually a rock like basalt or something else. So we'll get again a lot of this we're going to talk about with volcanoes, but we see that with this energy from time to time creating rock underneath the surface that may or may not make its way to the surface. Right? Here it talks about the transfer melting that can happen when heat transfer melting that can happen when you have a hot dome of magma rising and begins to melt rock around it. That's what we call heat transfer melting. So anyway, those are good to know. It's not going to be super important on the test. Always look at these pictures so you understand kind of how this whole process works. Now let's get into the question of what is this rock made of? What is this molten stuff? And your book describes it sort of as soup, melted soup. And that's a good way of putting it. So I was thinking of like a chicken noodle soup. If you think about it, it's got all these different parts to it. It's got some chicken in there. It's got some noodle in there. It's got some broth. It might have some vegetables in there. And so all those different things are kind of moving around as you heat the soup up. They're moving around and changing. And it's not until you maybe put the soup into the freezer that it stays in one place and becomes solid again. So chicken soup would be a good example. Now, how would that be different than, let's say, beef soup, right? Beef soup would look different. It's darker in color. It would have beef in it. It might have potatoes or something different in it. So what's happening then is in the magma, under the earth, we have pockets of literally different kinds of rock soup. And instead of potatoes and that sort of thing, we see some of the elements and some of the chemicals that can form in these soups. Things like silica, things like aluminum oxide, iron oxide, calcium oxide, sodium oxide, all kinds of different things that can form, that are formed, and that kind of float around in the soup. And so that's why in one area, if you had a volcano, you might get a certain kind of rock when the lava comes to the surface and the volcano erupts. But in another place where the soup underneath was different, had different chemicals, you might get a totally different kind of rock. And so that's what they're talking about here when they're talking about where these rocks come from and the major chemical types that we see. So let's look at these specifically, and this is a little bit important to look at. You're going to see the book talk about two different types of rock, or magma in this case. There on table 6.1, you can see it where they talk about felsic magma or mafic magma. Now, these two, you're going to see them a lot in the book, so you really need to know the differences. So felsic magma, or a magma that's high in silica, and there you can see the silica content, is just that. It has a lot of more silica in it. And again, remember, silica is basically that stuff at the beach, the sand at the beach. If you picked up a handful of sand at the beach, then about 95% of what you had in your hand is silica sand. And that's what we melt and make glass with. So that's silica. Now, mafic magma has more iron. That's where the FiC comes from, the Fic comes from, and magnesium. That's where the Ma comes from. and has less silica. There you can see a felsic magma has, almost 3/4 of it is silica, whereas by the time you get down to mafic, it's less than half. So these are the different types, and we'll see gradations of that. For example, you can get to ultramafic, right, where it has even less silica. So this is what you need to know, because we're going to look at this. This will determine the kinds of rocks that are formed from the different kinds of magma that come to the surface and form these rocks. All right. Again, these pictures are important. They help you a little bit with understanding how these rocks form. Let's see if there's anything else important here. Not particularly. So let's talk about 6.4 here, the movement and solidification of molten rock. So it talks about magma rising. So what would cause, why does a volcano form in one place and not in another place? In other words, why doesn't Kentucky have any volcanoes, right? So it's got to do with what's happening underneath the lithosphere, underneath the surface. So if you get an area where the lithosphere is thin, or where you have cracks, and that can happen through plate tectonics, right? We've seen that, or we'll see that. Yeah, we've seen that. Where we've talked about these places where we have plates that subduct and go under other plates and can cause volcanoes, because we see volcanic islands. So places like that, we would expect to see volcanoes. Whereas a place like in Kentucky, where we're in the middle of a plate, we wouldn't necessarily seem to see that, because we know in the middle of these plates are a lot thicker than the oceanic plates, right? We've seen that in the pictures, and so it's very unlikely that the material would be able to get up. But there are places where it's kind of weak, and we'll look at some of those. But it's all based on that material being able to rise, being able to come up and affect rock, melt rock, and then eventually make its way to the surface, or melt rock under the surface and create things like granite. So what controls the speed? So we've seen lava, right, in Hawaii that's moving almost like a river. I mean, it's moving so fast. And then we see other places where the lava is just creeping along, it just barely moving, might only move a foot an hour. Well, this has to do with viscosity. And if you've never heard of the word viscosity, it's got to do with the flow of liquid. So if something is viscous or very viscous or more viscous, then it tends to move slower. So, for example, the syrup you put on your pancakes is more viscous than water. I mean, if you put water on your pancakes, it would just run right off. If you put syrup on your pancakes, it tends to kind of stay there and kind of slowly go over the pancake. Toothpaste is even more viscous than syrup, right? If you put toothpaste on your pancakes, there might be a glob there, and you might not see it move at all, but you come back maybe in an hour or two, and it looks a little bit different. It's kind of moved out. So viscosity has to do with how a liquid moves. And we tend to understand that in terms of igneous rocks, right, that rocks with more silica are more viscous, and rocks with less silica are less viscous. So here we're going to transform melt into rock, and again, it has to do with what is in the rock and has to do with how hot it is. Obviously, a material that's very hot probably is less viscous than a material that's cooling down, and you've probably seen that with almost anything that's kind of hot, and then as it cools down, it tends to be more stiff and moves more slowly. And so not only can it have to do with what's in the material, what's in the molten material itself, but also the temperature. So it might come out really, really hot and flow very freely, but as that lava gets farther away from the heat source and begins to cool down, it probably slows down, and then of course eventually turns into rock. Now here's where it gets kind of interesting, because as rock cools, then what begins to happen is those chemicals inside the rock begin to form crystals. As you remember, we looked at many different kinds of not rocks but minerals, right, that formed crystals. And we saw what that meant, how minerals formed into crystals, how crystals literally grow. They don't grow like a plant, but they do get bigger and begin to take shape as more and more of the material kind of comes together. It forms in that particular shape based on the molecular structure of whatever chemical it is that it's forming. And so that's what we call crystallization. And so, if you remember from the two rocks that I showed you just early on, when I showed you the rock that was extrusive, right, it cooled very quickly. Well, we didn't see many crystals at all, did we? I mean, it just kind of looked like a brown glob. It looked like everything was kind of all globbed together, right? Well, there are crystals in there. There is a lot of those chemicals in there, but they never had time to crystallize because the rock cooled so quickly. However, if you also remember, when I showed you the granite, you could see individual crystals, couldn't you? You could see little black specks, and you could see little green specks, and you could see little white specks. Well, those are the individual crystals that were beginning to grow. And so if I were to show you on a test different kinds of granites and ask you which granite cooled the fastest and which granite cooled the slowest, well, all you'd have to do is look at the crystals, wouldn't you? Because the granite that had the bigger crystals, right, must have cooled slower because those crystals had time to grow and get bigger, didn't they? And the granite with the smaller crystals must have cooled faster because its crystals were smaller. They didn't have quite as much time to grow. So that's where this crystallization gets kind of interesting, because not only can it tell us what's in the rock or what's in, what chemicals and what minerals are in the rock, but it could also tell us kind of where that rock became a rock. You could almost argue that a rock that has larger crystals, where the rock cooled slowly, was probably deeper in the earth, wasn't it? And a rock that probably has smaller crystals may have been not as deep in the earth, or at least farther away from the heat source, that original magma chamber, to cool quickly, and therefore not give the crystals time to grow. So that's kind of an interesting little story about each of these rocks. So that my big bowl of granite, that's what's kind of fun about my big bowl of granite. I can look in there and see all these different kinds of rocks and realize that they all came from Maine, right? But literally, they all came from different parts of the earth. I mean, some of them were deeper, some of them not so deep, and all of them formed in different ways. So it's kind of neat when you stop and think about it that way. We're looking at different kinds of environments here. Extrusive environments obviously are above ground. This is lava turning into some kind of a rock, igneous rock, depending on what it's made of. Then intrusive environments can be a lot more interesting in that you can have, again, rocks that are closer to the heat source that cool slowly, can have large crystals, and rocks then that cool farther away from the heat source can have smaller crystals as they cool faster. Now, in terms of extrusive rocks, we didn't get into too much about other kinds of volcanoes. In other words, my extrusive rock that I showed you here, the shiny glass rock, probably came from lava, but of course we're going to learn in Chapter 9 that volcanoes can also spew out ash. They can spew out other kinds of rock in different sorts of characteristics. And so those also are extrusive igneous rocks, and they look very, very different, or can look very, very different than my piece of obsidian. So again, here are some more pictures of some of this. Again, a volcano here that is exploding, not just a nice flow of lava like we see in the picture on the left. Here we can go back and look at lava flows from the past, looking at where these were, how thick they were, how big the eruption was, all sorts of things like that. So it's all very interesting. Don't worry too much about Dr. Bowen's reaction series. It's a little, I mean, read it definitely, and kind of it is very interesting, but it's not anything we're going to get into in too much detail. So again, talking about describing igneous rocks, of course, any kind of rock, there's different ways of describing it. We've got color, we've got texture, we've got its mass, whether it feels heavy or feels light. And then, of course, we can get into what crystals and what chemicals are involved in it. And so there's lots of different ways to describe these kinds of rocks. Igneous rocks are most interesting, and again, can be described basically as extrusive igneous rocks and intrusive igneous rocks, and they have very specific characteristics that we already kind of talked about a little bit. Now, granite is kind of interesting because we didn't get into this in too much detail about the formation of the Earth, but continents, places where we live, exist because of granite. In other words, they were formed, we think, about 4.2 billion years ago, not too long after the formation of the Earth, as water kind of got into the Earth and cooled some of the magma rather slowly, creating, rather than basalt, which is what we see on the ocean floor, but rather this very hard but much lighter material, granite. Now, I say lighter, of course, it's a rock and it feels heavy, but relatively lighter than things like basalt or things like other extrusive igneous rocks that are much more dense and much heavier. And so the continents literally, as the Earth is forming, the continents in this lighter rock literally float. I mean, again, that sounds kind of crazy that rocks are floating, but this granite, since it is less dense, it is floating on top of this what we think of as oceanic plate now, floats on top of it. And so that's why the continents are kind of sticking up and the oceans are around us, is because if you dig almost anywhere, you're going to hit granite. If you dig anywhere on dry land, you're almost always going to hit granite. Now, here in Kentucky, of course, the granite is pretty deep because on top of the granite is a whole bunch of limestone, because here in Kentucky, this used to be almost the whole state, used to be the bottom of an ocean that not only had oceanic lithosphere, but also animals. And so that's where the limestone is going to come from. We'll talk about that when we get to sedimentary rock. But most of Kentucky, if you start digging here, what you're going to hit is limestone, and that's living organisms. Those were the leftover shells and the calcium and material left over from organisms. And it can be very, very deep. You'd have to dig pretty far down and through the limestone here in Kentucky to eventually hit the granite. But in some places, like here out in California and Maine, like I said, I found all my granite out in Maine. There's big chunks of this granite that are just sticking up because they didn't have the limestone that we had. And so you would find granite right there on the surface. And there's lots of places in Kentucky where you might see some granite too, where the limestone's been eroded away. But for the most part, like I said, if you do dig here in Kentucky and hit rock, you probably just hit some limestone. All right. Again, we're looking at formation of igneous rocks, and I want you to read through this definitely. And look at these pictures, how these rocks are formed. But a lot of it won't specifically be on the test. But some stuff, like looking at these rocks here, I might ask you about these kinds of rocks. There on the right, you see a piece of obsidian, which is what I just showed you, right? The extrusive rock, that glassy rock that was formed as an extrusive rock. But on the left, you see granite, an intrusive rock that was formed slowly. You can see where the crystals were growing there, and that's kind of how you can tell them apart, can't you? So definitely, in terms of classifying these rocks, definitely read this section and understand that, because that probably will be, it is important, especially for the test. Here they're comparing some of the different types of rocks. Again, the mafic rocks versus the felsic rocks. And again, the best way to kind of keep these separate is remember that Ma and FiC stand for magnesium and stand for and that's hard, I understand. But the FiC stands for iron. Iron on the periodic chart, as you remember, is not an I, but an Fe, isn't it? Because the periodic table, when it was first created, was all done in Latin. So the earliest elements all have sort of Latinish names as opposed to common English names that come along a little bit later. And then, of course, felsic rocks, remember it's that last three syllables, the SiC, the silica, that is the thing that will tick you off. You'll understand as the two. This is a good one to look at too, as to types of rock and what they're made of. That will be helpful just to kind of keep that in mind. And then here's some of the different types of rock. I've got some pumice, which is pretty interesting. Pumice, if you've never seen it, and you have seen it, pumice is used for lots of things. There used to be a soap, and I think I'm sure you can still buy it. I remember as a kid, my dad worked on cars, and he had this soap called Lava Soap. And Lava Soap was terrible because it had this scratchy stuff inside of it. And Lava Soap actually had little pieces of pumice, and the idea was you literally scratch the dirt off your hands with this pumice. It's very, it's glassy, but it's got lots of holes in it where the gases came out. As a matter of fact, it's got so many holes in it like a sponge that pumice is the only rock that will float. So I usually used to do this in class, and again, I can't do it because you're there and I'm here. But I'd bring in some pumice and a little thing of water, and we'd watch rocks floating, which is pretty amazing. There's a good picture here of different types of rock and their silica content, what they look like. And there's a piece of pumice right there on top of the $20 bill. It's pretty cool because a great big chunk of this stuff just feels like it's made of paper, because it's got so many holes in it. So how does plate tectonics tie into all this activity? Of course, plate tectonics is a result of this volcanic activity. We've already talked about the subduction zones that create the volcanic arcs, or island arcs in the Pacific near the trenches where the plates are submerging underneath other plates, not to mention volcanoes. Now, we talked about the fact that there wasn't a volcano in Kentucky because we're right in the middle of the plates, but we do know there's places where we have volcanic activity in the middle of the plates, don't we? If you've ever been to Yellowstone National Park, we'll talk about that definitely when we talk about volcanoes. But Yellowstone National Park, when you're in the park, you're actually in a volcano. And so it is near the edge of a plate, but it's not on the edge of a plate. So there are these super volcanoes that we'll talk about a little bit later. But again, these things can form any place there's kind of a weak spot in the lithosphere, and that magma material can make its way to the surface. So here's a map of some of these hot spots. And again, you can sort of see, if you look at the United States, there is a big chunk of Yellowstone. And you also see places along the eastern seaboard where we have old volcanic activity, big chunks where that was. And as you can see, it kind of runs along the Appalachian Mountains. And so the formation of those mountains a little over 1 billion years ago probably created an awful lot of stress and pressure to create some volcanic material. Oh, interesting stuff here. And then, of course, getting into your questions. Now, the only last thing I wanted to say was about my, I usually ask students where they think I got my my big piece of obsidian, this glassy rock that I showed you first. And no, I didn't buy it in a store, and no, I didn't find it near a volcano. I found it here in Kentucky. And so the question is, well, we don't have any volcanoes in Kentucky. How did a big chunk of magma, or what was literally lava that cooled, how did that get to the middle of Kentucky? And when we get to glaciers, we'll talk about how glaciers move some of this material very far. And this big chunk of frozen lava probably came to us from a glacier, which even makes it even a cooler thing. So that is pretty much everything I have for igneous rocks. Again, make sure if you got any questions about some of this stuff, make sure you use the grapevine thing at the end of these units. That's kind of what I'm looking at, and also make sure if you got something, I check those periodically, but I check my email all the time. So if you got something that's a burning question, shoot me an email, and I'll be happy to help you out. Have a great weekend, and I'll see everybody next time.